Hi friends, welcome to my channel Code and Canvas, and in this video we are going to learn about HTTP2. Before starting the video, I just want to make a small announcement. As you know, I also make sketching videos. So if you are interested in sketching, I will be moving all my sketching videos to a new channel, Shades and Canvas. I will I will post the link to the channel in the comments as well as in the description. So all the future videos will be posted on that channel only. So let us start. As from my previous video, you might have already know that HTTP1 suffers from several issues. One of them includes head of line blocking. So as you know, for every request, HTTP1 creates a TCP connection, right? So on a connection, only one request can be sent at a time. For example, if HTTP1 wants to use a connection to send multiple requests, it needs to wait for a request to complete before sending another request. It cannot send multiple requests parallelly on the same connection. If it wants to make multiple requests parallelly, it needs to open multiple connections as well. Another is redundant headers. Redundant headers here means for every request there are some headers that will be same always. For example, method header will be present in all of the requests with get value. So for example, if you are visiting on a page, there can be many calls to a server, right? Multiple calls will be being made to the server, and in each request there will be some headers that will be common. For example, content type and method and various other headers. So they are repeated in each request. Many TCP connections, as I have already explained, for multiple requests in parallelly, it needs to open many TCP connections. So it's also there. Slow loading on high latency networks. So if the latency is high, loading will be slow, because if the latency is high, it will be waiting. Many of the requests will be waiting for the response from the servers, and the loading will be slow. It needs to use multiple connections to achieve concurrency. Obviously, for parallel request, it needs to open multiple connections. Also, it does not compress any request or response header. For example, when it sends data to the server or vice versa, it doesn't do any compression. It's just a plain text format. Like all the headers as well as your body will go in a text format, and there is no compression or any optimization on that part. So it also does not allow any effective resource prioritization, result in poor use of underlying TCP connection. So on HTTP1, for example, if you want some resource to be get some priority over others, or some request to get some priority over other requests, it cannot be done there. There are some resource hints that can give you the resource before page load or make the connection before, but it cannot set priority on different requests, which is an option in HTTP2. We will look into that later. So the primary goal of HTTP2 are to reduce the latency by enabling full request and response multiplexing. We will come to know what this multiplexing means, but basically in multiplexing, HTTP2 can send multiple requests and get response for those requests parallelly without waiting for the first request to get completed. Minimize protocol overhead via efficiency compression. So here HTTP2 has introduced compression of the HTTP headers. Like it is not based on plain text format. It just compresses the header using some compression algorithm and then sends them. So it also adds support for request prioritization and server push. We'll look each of them in detail and further in the video. So HTTP2 does not modify application semantics and HTTP in any way. So the advantage on HTTP2 here, like it does not modify any semantics of HTTP. For example, methods. All the methods that are present in HTTP1 are there in HTTP2. All the headers that are present in HTTP1, they can be used in HTTP2 as well. So your request body, your methods, your headers and everything which forms the structure of a request is still same. You have to just pass the same headers, same body, same methods, and everything is still same, URL and everything. The only way that is different from HTTP1 here is how it sends data. So earlier in HTTP1, it was opening a single connection and it was sending data in packets and text-based format, right? It was not encoding anything. Only the way data is sent using compression, or the way data is traveled between a client and server or vice versa, it differs. So there is no change on the outer layer of the protocol. The internal transmission has differed. So HTTP1 is a text-based, but to achieve the performance goal set by HTTP working group, HTTP2 introduced a new binary framing layer that is not backward compatible with the previous HTTP1. What does it mean? So HTTP1 is text-based, right? So in HTTP2, they have introduced a framing layer called framing. So we will look into about this in detail. basically in HTTP2, now request and response uses a frame structure to send data from client to server and vice versa. So as the internal working is different from HTTP1, so HTTP2 is not backward compatible with the HTTP1 request. So your both client and server, both of them should support HTTP2 request. Otherwise, it will not be able to communicate between client. Communication will not be able between client and server. You cannot send a HTTP1 call to HTTP2 server, as well as you cannot receive response on a HTTP2 client from HTTP1 server. So both need to support HTTP2. This is not a backward compatible protocol. So it enables more efficient use of network resource and a reduced perception of latency by introducing header fuel compression. As I have already told you, like there are now compression while sending the headers and the data. So it reduces latency, and it uses more network resources more efficiently, because compression reduces the size and everything. We will look about that. So let's start deep diving into the features of HTTP2 one by one. One is binary framing layer. So here the semantics are same about the verbs, methods, headers. These are like unaffected. The way they are encoded and while in transit, it's what different in the HTTP2 protocol. So here, unlike the new line delimited plaintext HTTP1 protocol, all HTTP2 communication is split into smaller messages and frames, which are either encoded in binary format. So earlier, as you have seen in the HTTP1, headers and everything was sent as a text base. Now all the communication that is being happening in HTTP2, whether it is a header being sent from client to server, data being sent from client to server, and vice versa, every communication that takes place between client and server, that is divided into small frames. So for example, let's say you are making a request from client to server, right? So here, as you can see in this diagram, in the application layer, there is a framing present. So in the framing, there could be different frames present for different parts of the request. For example, a request can have a header and a data, right? So in the header, in HTTP1, all of this will be present in a single packet, or you can say single communication packet. So it contains headers and message and everything, right? But in HTTP2, this will be sent in different frames. So HTTP2, for example, will create a separate frame for header and a separate frame for data. So both of the frames will travel independently from client to server, and while getting the response from server to client, same thing will happen. There will be a separate frame for header and separate frame for data, whatever response the server is sending to the client. And in both the sides, when the frames are received, they are assembled together using the ID, and after assembling them, the server or clients comes to know about the full request details or full response structure sent by the server or client. So we will look into the more details about this frame, how this frame is structured. There is a frame ID that is present in metadata of every frame, that is actually used to find out this frame belongs to which request. So let's move forward. So stream, messages, and frames. These are few terminologies that you must know if you are learning about HTTP2. A stream is a bidirectional flow of bytes within an established connection, which may carry one or more messages. So think of it like a pipe. So when a connection is made between a client and server, there can be multiple streams. It can open multiple streams into it. One connection can support multiple streams, and each stream it is just a bidirectional flow of bytes from client to server and vice versa. A server can use the same stream to send the response, and the client will use the same stream to send the request. So message is the complete sequence of frames that maps to the logical request or response message. So as you have seen here in HTTP2, instead of sending everything in a single message, headers and everything, it is divided into different frames. Header is sent in a different frame, data is sent in a different frame. So a frame is a part of the request, some data that is necessary for the request. And when we collect all those frames and we combine them, we get a message. It's a complete sequence of frames, like header should be on the top, data should be at the bottom, things like that. When we assemble all the frames in a logical way, we get the message. It works for both request and response. Frame is the smallest unit of communication in HTTP2. So each containing a frame header, which at the minimum defines the stream to which the frame belongs. So here in this, let me see. So for example, let's say there are multiple streams that could be open for a TCP connection. So when a request is sent from client to server, or vice versa, when a response is sent from server to client, in all the cases, the message, the complete request or response will be divided into different frames. And as a message is broken down into multiple frames on the client or the server side, there should be something present in each frame to know what frame belongs to what request or response, so that it can be assembled in such a manner. So when the multiple streams are open, for example, let's say first request was made by client to server, a stream will be open, and that ID of that particular stream will be sent in each frame that belongs to that particular request. Similarly, the next frame, when the next request will be made, another stream will be open using the same TCP connection, and the stream ID for that stream will be present in all the frames that belongs to the second request. Similarly, when the server will get the request frames, server will receive the frames from the streams. It will just assemble according to the stream IDs. Using the stream IDs, it will know these frames belongs to a single request and these frames belongs to another request. When it gets all the frames, it does some processing, it gets the data from DB or somewhere, then it sends the response in the similar way. The HTTP2 will divide the response in different frames, header in a different frame, data in a different frame, things like that, and then it will send it to the client. The client will use the same mechanism. Using the stream ID, it will know that whatever stream ID have sent in the request, same stream ID will be present in the response for that request. So a request response pair uses the same stream ID. So by that, the client will come to know that this response belongs to this request I have made, and using the stream ID, it will collect all the frames coming from the server for that particular request, and in the end, it will know that what response has been sent by the server. So basically here, as you can see, everything else is same. For example, while making the call, everything is same in HTTP2, methods, headers, and everything is. The only way that differs here is how the data is traveled between a client and server. Here it was a simple TCP connection, but here we are opening different streams within a single TCP connection. So this helps us in multiplexing. So how it helps in multiplexing, let's see. So for example, let's say in HTTP1, as we know, there was head of line blocking in HTTP level, right? Because for example, in a single connection, you can only make one request at a time. If you want other requests to go in parallel, you have to open multiple connections. And in a single connection, once a request gets completed, the response is get by the client. Only then the another request can go through the same TCP connection. But here, as we are not depending on the response of a previous request, because here data is sent in a frames and every frame is independent of each other, and server and client both can identify using the stream ID what frame belongs to what request or response. So here you can send multiple requests and response uh, without waiting for a request to get completed. For example, let's say client client is sending some data to the server and server is sending the response. So as you can see here, server is sending the response for two different requests. So as one request response pair belongs to a particular stream, as you can see there are two different stream IDs present here in the data that is coming from server to client, stream 1 data and stream 3 headers and data. So for example, data could be big, right? So there can be multiple data frames. So if you have a huge JSON, it might not be a good fit in a single frame. So there can be multiple frames for data as well as headers, depending on the size. So here, as you can see, the data is coming for both stream 3 as well as stream 1, basically the request 3 and request 1. And they are interleaved, they are not in sequence. So first the partial frame of data, partial frame of stream request 1 is sent, then the frames for stream 3 are being sent, then again the frame for stream 1 is being sent. So it's not in sequence, like only after the stream 1 is sent the stream 3 will start. There can be interleaved data between them. It doesn't wait for a request to get completed or a response to come back before making another request. It will just start opening new streams based on the request and response, and it will just send the data in frames independently. And once a client or a server receives all the frames that belongs to a particular request or response, it assembles them and comes to know about the data that is sent through client to server or vice versa. So that's what I have written here, I guess. The new binary framing layer removes these limitations and enables for request and response multiplexing by allowing the client and server to break down the HTTP message into independent frames, interleave them, and then resembles them on the other end. So that is what I have explained just now. The ability to break down an HTTP message into independent frames, interleave them, and then reassemble them on the other end is single most important enhancement of HTTP2. So the benefits for this are: interleave multiple requests in parallel without blocking on anyone, because you don't have to wait for a request or response before starting a new one, as every frame is independent of each other. So you can just interleave whatever data you want to send. You can just create a frame out of that and send it. You don't have to wait for any other thing. Interleave multiple responses in parallel without blocking on anyone. Same thing for the server. Use a single connection to deliver multiple requests and response in parallel. So as in HTTP1, we were creating multiple connections to make parallel calls. Here in the single connection, we are making different parallel streams, and we are using those streams to send multiple requests and responses. So we don't have to open multiple connections again and again for parallel request. Remove unnecessary HTTP1 workarounds or concatenated files, image paths, and domain sharding. So it's not needed here because we are using single TCP connection to do everything. Deliver lower page load times by eliminating unnecessary latency and improving utilization of available network capacity. So obviously, as we are not waiting for request to make another request, and we are using frames and single TCP connection, resource utilization is better than HTTP1. Also, the latency may also reduce. So if one of the resources taking more time, other resources will not be blocked. They can still go in parallel and fetch the data for them. Once the big resource is ready, it will come whenever it is ready, but the page will not wait for that resource anymore. So stream prioritization. So this is one of another feature that is provided by HTTP2, stream prioritization. In this, actually, you can prioritize streams as well. So you can say that this stream has more priority over other streams, so it should be given more importance. I mean, more resources and all those things. So let's look into it details. So here, each stream is assigned an integer weight between 1 to 256, and each stream may given an explicit dependency on other stream as well. So here are two ways by which you can provide a stream a priority. So you can either assign them a weight. For example, let's say there are two streams open, and you can assign them different weights, one or let's say two on another, or you can say that stream 2 is dependent on stream 1. So stream 1 will be given more priority over stream 2. So it allows the client to construct and communicate a prioritization tree that expresses how it would prefer to receive the responses. The server can use this information to prioritize stream processing by controlling the allocation of CPU, memory, and other resources. So using this information, either the weights or the dependency tree that it is creating using the config, it will just decide how the resources are divided between different streams. So let's take into some of the examples. So our first case. So if in this case, let me tell you one more thing. So when you give a stream a dependency on another stream, you tell it using identifier. Tell it using the identifier of the other stream as its parent. So you say, for example, the ID of stream A is 12 and ID of stream B is 4. Then if you want B to dependent on A, you will tell using the stream ID that this is the parent stream for B. So that's how you would say that B is dependent on A. So if any parent stream ID is not given in a particular stream, then by default it goes to the root stream. Root stream is the for example, parent of all. So it default value you can say if you do not provide any parent stream ID. So here, as you can see, A and B they are not dependent on each other, right? So they are under initial root stream. So default is going to the root. but the weight is different. So A has a weight of 12 and B has a weight of 4. These are weights in the image, like not IDs. So these are the weights for a stream. As the weight is different, so based on the weight, we will receive 1/3 of the resources allocated to stream A. So as the weight of A is more and B is less, and it's 3 times less, right? So let's say if A gets 100 CPU, B will get 1/3 of that, around 33 CPU. So the resource distribution is according to the weights. If the priority is on the same level, right? If they are not dependent on each other, then the distribution of weights, if the streams are open in parallel, it will be according to the weights of stream. Now, in this case, um, D is dependent on the root stream and C is dependent on the D. So as you can see here, D is dependent on the root and C is dependent on the 8. So when these will open, so as they are not parallel, right? So C is only dependent on D. So D will get full resources. When D is completed, C will get all the full resources because there is nothing in parallel, right? So here the same thing, D is dependent on the root, C is dependent on D, and A and B are dependent on the C. So D should receive full allocation of resources ahead of C. C will receive full allocation of resources ahead of A and B and A will behave as parallel streams, and the resources will be divided among them based on their weights. So once the D is completed, C will get all the resources, then they will be distributed among A and B will get 1/3 of the resources that are allocated to A. Same here actually. So here E and C are dependent on D and D is dependent on the root. So D will get full allocation of resources. Then resources will be equally divided between E and C because weights are same. Then after C is completed, and whatever resources C will release, or maybe let's say E is also completed, then whatever resources are released, those will be divided between A and B based on their weights. Okay, server treats prioritization as a hint, not a rule. So server receives priority information in the headers or priority frames, but it can ignore it as well. So client can set their own priority or something, but if server has their own rules regarding the priority that it doesn't want to be overridden by the client, then it can ignore it as well. It also depends on the config. So if the server does respect priorities, it usually maintains a stream dependency tree internally. So when the server respect priorities, it will maintain this kind of dependency tree, and based on the tree, it will find out what resource and to be allocated to which stream and when to allocate it to the particular stream. So it uses a weighted scheduling algorithm. So as we have weights here as well, right? So it can use any weighted scheduling algorithm like round robin or something, weighted round robin or something, with to find out which stream to send next and how much data from each stream to send. A high priority stream can still be blocked by flow control limits and disk or backend latency. Flow control we will learn about in the further in this video. But disk or backend latency means, for example, if a stream has higher priority, but its underlying tasks are taking time. For example, data reading data from the disk or maybe some getting data from other services taking time, then it can still block the high priority stream, right? So it depends on that as well as the flow control limits that are being sent by on a particular stream. One connection per origin. This is same actually because we don't need multiple connections per origin. As in HTTP, when the limit was 6 on a browser, right? It can open max 6 connection per domain for parallel request. Here it's not needed. Only one connection is needed, and we use multiplexing and interleaving frames to send multiple requests and responses over a stream. So the cons here are TCP head of line blocking. So if you have seen my previous video, I have explained TCP head of line blocking there. So it is still there in HTTP 2. The head of line blocking that is being resolved here is HTTP head of line blocking, in which one connection can be used again and again without waiting for a previous request to get completed. But here TCP head of line blocking is still there. So in TCP head of line blocking, the data is being sent in packets here as well, right? Because in the underlying protocol in HTTP 2 is again TCP. So data is being sent in TCP packets only, whether it is compressed or not, it is being sent in TCP packets. So even if the multiple streams are independent, streams and frames are independent of each other, let's say if one packet is lost, so the other packets will not be sent until unless that packet is resent by TCP, right? This is how TCP works. So TCP head of line blocking is still there because once a packet is lost, until unless it gets retransmitted, other packets will not be sent and all the streams will get affected by it. Bandwidth delay product limitations. So bandwidth delay product is something called bandwidth into round trip time. It represents the amount of data that can be sent in flight before waiting for acknowledgements. So there is something called bandwidth delay product limitations where you can set some amount. For example, in TCP, it gets acknowledged, right? Whenever it sends a packet, there are acknowledgements being sent, right? So it represents how much data you can send in the pre-flight request before waiting for the acknowledgement. So if TCP window scaling is disabled, then for example, it is disabled, like it doesn't say don't send any data before waiting for acknowledgement, right? Then the connection will get underutilized because it will only send data after getting the acknowledgement from the receiver, right? So the connection can get underutilized and throughput can be kept easily on high latency bandwidths. Like so, if you have high bandwidth links, for example 5G and 1 Gbps link, then it will behave like 50 Mbps, right? Because TCP is not allowing you to send more data. So if there is a limit on the TCP side, like you cannot send more than 50 Mbps. But if your pipe or if your bandwidth allows you 1 Gbps, it will not matter, right? Because TCP has a limitation on there. So it will not matter how good your internet is or how much data you can send on that connection. It will always behave like a 50 Mbps because of that limit. TCP congestion control. So when a packet is lost, TCP assumes network congestion. It reduces the congestion window and slows down all the streams sharing that connection. So when a packet is lost in TCP may assume that there is more traffic going on. This more traffic going on than the server can handle. So it assumes that there is a congestion in the network, and it can reduce the congestion window. This same limit, it can reduce the limit, and then it will slow down all the stream that will be sharing that connection, right? So this is one of the one more con that can happen here. So this is just a small example I have taken in case of packet loss. Let's say the client is sending 4 packets, which is HTML frame, image frame, CSS frame, and another HTML frame, which is basically the continuation of the first frame. So let's say CSS frame is lost somewhere in the mid transmission. So TCP level reaction, TCP won't deliver packet 4. So as 1 or 2 are already gone, it's waiting for 3, which is not received, right? So TCP won't deliver packet 4 as until irrespective of this packet of frame is contains data that is independent of the packet that is lost, right? CSS and HTML are independent of each other, right? Like they are separate resources. So even if the data or the resource that is present in a packet is independent of each other, it will still stop the transmission of packet 4. So HTTP2 will get stuck and it will not process any stream whose frame was in packet 4. So all the streams will get stuck until unless the packet 3 is retransmitted and acknowledged. This will create a problem of head of line blocking at the TCP level. So HTTP3 has a solution with this because HTTP3 uses QUIC protocol, which uses UDP, not TCP. So in UDP, as TCP maintains the consistency, right? Like it guarantees the delivery of the packet, but UDP does not, right? So we will look in more detail in a separate video on HTTP3. I will be creating a separate video on HTTP3. We will get into more details about it in there only. But it resolves this problem using the UDP protocol. Now let's look into the flow control. Flow control is a mechanism to prevent the sender from overwhelming the receiver with the data it may not want or able to process. So your connection can allow, let's say, 1 Gbps data to transfer from a server to client or vice versa, but your receiver cannot handle that much amount of data, or it doesn't want that much amount of data for some certain reason. For example, let's say the client may have requested for a large video stream with high priority, but the user has paused the video and the now client wants to pause or throttle its delivery because the user has paused the video, right? So it is not effective to fetch the remaining video from the server until unless the user resumes the video, right? So in that case, client wants to tell the server that stop sending the data for this video. So flow control can be used for such purposes. There are two levels of flow control in HTTP2, which is connection level flow control and stream level flow control. The connection level flow control, the entire TCP connection has a global flow control window, and it limits the total amount of data sent across all streams. Since the connection can have multiple streams, so it puts a limit on the total data that can be sent across all streams. It helps the receiver message. It helps the receiver manage memory pressure and avoids buffer overflows. Another is stream level flow control. So apart from connection level flow control, a stream has its own flow control as well. So in each stream, you can say how much data can be sent on that stream at a particular amount of time. So both of them work with together. So if let's say if your connection level flow control says 10 mbps and your server level flow control can say 5 mbps, then on a particular stream only 5 mbps of data will go, but on the total connection on a TCP connection combining all the stream, 10 mbps data can go. This control how much data can be sent on the specific stream before waiting, prevents one stream from hogging the bandwidth and blocking others. So it prevents the stream level flow controls also prevents the stream uh, to use all the bandwidth that is present and blocking the others, because you can say it can only send this much amount of data, so all the resources will not be used by the stream. So flow control frame, there are frames that are present to update the server about this, which is window update frame. It is sent by the receiver. Receiver can be client or server. So if server wants to send update the limit on the flow control, it will send the frame to the receiver to the client, or if the client wants to set up the flow control, it will send the frame to the server. It tells the sender you can now send X more bytes on the stream or connection. Updates the flow control window size. So basically in this frame you have all the information that is needed by the sender to update the flow control settings. So it will just it tells you it basically tells the sender that you can send these many more bytes on the stream or the connection, and also updates the window of the flow control size. So let's say let's take an example. Let's say you have a stream level window of these many bytes, 65,535 bytes, and connection level window of 65,535 bytes. So as you can see, both of the limits are same. And let's say sender wants to transmit 30 KB data on stream A and 50 KB data on stream B. So what will happen here, because the total data is more than the allowed by the connection level window, right? So this is like 80 KB, right? But the amount that is allowed on a connection level is around 65.5 KB, right? So this 30 KB data will be sent in the stream A, because single stream also allows 65.5 KB data, right? Which is greater than this limit. So 30 KB will be sent on stream A, but from the remaining 50 KB, only 35.5 KB is sent on stream B. Although the flow control on a particular stream is greater than 50 KB, but as we have a total limit of 65.5 KB, only 35.5 KB of this 50 KB will be sent on stream B, and remaining 40.5 KB of the stream B is blocked until the receiver sends a window update frame. So once the receiver gets this much amount of data, it will send a window update frame saying send me the remaining 14.5 KB data, and then only this data will be sent on the connection. Another feature provided by the HTTP is server push. So basically in server push, a server can send multiple responses for a single client request. For example, let's say you want a HTML file, right? Let's say you make a request to get some HTML file, but server can decide that along with the HTML file you will need the CSS and JS also, and it will just send those as well in the response using frames and all. But this server push is not not supported by HTTP2 and browsers anymore, because it's a bit complicated to implement. So despite sounding promising, many CDNs and browsers have deprecated it. Chrome has deprecated it in 2022, and HTTP3 and Quick also have dropped the support for it. Also, many CDNs do not recommend it anymore, because it was hard to use well. Because most of the time it was just wasting your bandwidth. For example, let's say if server sends you some extra data which your client may not need at that point of time, then it will be just wasting your resources, right? And it will just hogging the streams and everything. So this was dropped in the HTTP2, and there are alternative approaches for this, which are like preload or prefetch. These are resource hints which you can read about them. Basically, it tells you it just tells the browser to prefetch or preload some data based on the configuration provided in the HTML. So in your HTML you can provide these hints, and based on them, browser will either prefetch your data or preload the data before it is actually needed, and it's way easier to use than this server push. So let's move to the last part, which is header compression. So as we know, in HTTP2, the headers are compressed and not sent as a text in the like in HTTP1. So as in HTTP1, for example, headers like get, host, user agent, accept, and cookies. These headers are almost present in every request. So for same daemon, the values for these headers will be same as well. So these headers also grow large with cookies and user agents. So values on cookie can be huge, right? So these headers can grow in size as well. So HTTP2 uses a small compression format called HPAC for header fields. It makes header transmission smaller, more efficient, and faster. Let's see how HPAC is used to compress the headers. So it contains two tables, which are static and dynamic header tables. Static tables contains all the common headers like method, path, which are like common in all the requests. Those are present in static table. And dynamic tables store the headers that it is seeing during the connection. For example, content length, content type. For example, they can be different for different requests, right? Content type can be JSON or XML. They can be different for different requests, right? So dynamic headers are built during the connection once the request or responses are received by the client or server. When a header is already in one of the tables, the sender just sends the reference for that header. So let's say in the static tables, these kinds of header will already be present, right? And the other headers, which are dynamic and different for each request, they will be sent when the request will be made or when the response will be received by the client, right? So whenever it gets a new header in the request or a response, it makes the entry for that header in the dynamic table. And if the header is already present in a dynamic table or a static table, it will just send the reference to that header instead of sending the header and its value in the request. So let's say for all these headers, if they are already present in the static or dynamic table, instead of sending all of them in the separate request, it will just send the reference to the header in that particular table. For example, let's say get is present at index header field 2. It will just send that in the get the header from this particular index in the table. Similarly, get a header from this particular index in the table. So it will mean method is get and it will mean scheme is HTTPS. So that's how it compresses it reduces the size that is needed for the headers. So HPAC uses Huffman encoding to encode all the header values. So if you know about Huffman encoding, then you know that in this, for every character we generate a code, and each code is unique to each other. So whatever codes are generated for a character, they will not be a prefix of any other code. I will be creating a separate video on Huffman encoding, but for now, let's say there is a string called ABCC. Then one possible code that can be generated from Huffman coding, A will be treated as 0, 1, B will be treated as 0, 0, and C will be treated as 1. As you can see, none of the encoding is a prefix of another, right? So it's easy to decode. So that's why it is easy to decode once the content is encoded. So string that will be transferred instead of ABCC is 0, 1, 0, 0, 1, 1. So here, as you know, each character takes a byte, right? For example, each character takes 8 bit. So here, instead of sending 8 for the 32 bits of data, we will be sending only these many bits. And while decoding, we can easily figure them out. So 0, 1 belongs to A, 00 belongs to B, and 1, 1 belongs to CC. So because none of the encoding is a prefix of another, it's easily decodable. The problem here is compression dependency and head of line blocking again. So let's say stream A sends a header with new entries in dynamic table, and stream B sends header that reference to those entries. So let's say there are some headers that are not present in the table right now. So in the stream A, let's say we are sending those headers to add those entries in the dynamic table. And in stream B, let's say another request is being made, and it is using those headers as, let's say, the client has already sent the frame to add those entries in the dynamic table, right? It will just send the indexed values for those new entries. But let's say for somehow the packet that was sent in stream A got lost, then stream B cannot, the data that is sent in stream B cannot be decoded unless the packet of stream A is retransmitted and received by the server, right? And the dependency and the dynamic table is updated. So it will wait for that packet until the request is fulfilled. So this creates a head of line blocking here. So HTTP3 uses a new compression scheme called QPAC, which is optimized for multiplex streams over QUIC. QPAC resolves the head of line blocking issues present in HPAC. We will get into more details about this in the HTTP3 video. So this is how a frame looks like. So frame this is how the data is present in a frame. So the 24-bit length allows a single frame to carry up to 2 to the power 24 bytes of data. So in this, the frame contains 32 bits. The first in the first line, first 24 bits represents the length, how much data, the length of the data, how much data is present in the frame. So as the length of this field is 24 bits, the total data that can be present in a frame can be up to 2 to the power 24 bytes. The next 8-bit type determines the format and semantics of the frame. There can be different type of frames, right? That data frames, which contains the data, header frames, priority frames. So this field represent what type of frame is present. Then the 8-bit flags communicates frame specific boolean flags. There are some flags that can be used for different purposes. This field represents the flag. Then this is reserved for this is always set to 0 and this is a reserved field. Then the 31-bit stream identifier uniquely identifies the HTTP2 stream. Now this field contains the stream identifier for to which stream the frame belongs to. So as you know, while sending a frame, we also send an identifier, so which server or client uses to figure out what stream the frame belongs to, and uses this identifier to assemble all the frames that belongs to a particular request or response, right? So this is the same identifier. Now there are different types of frames that can be present in HTTP2. A data frame, which is used to transport HTTP message bodies. Header frame, which is used to communicate header fields for a stream. Priority frame, which is used to communicate sender and advise priority for a stream. RST stream, used to signal termination of a stream. Settings, used to communicate configuration parameters for the connection. Push promise, used to signal a promise to serve the reference resource. Ping, used to measure the round trip time to perform the liveness checks. Go away, it is used to inform the peer to stop creating streams for current connection. Window update frame, it is used to implement flow stream and connection flow control, as we have seen earlier. And communication frame, used to continue a sequence of header block fragments. Now I have created a table which displays the differences between HTTP1 and HTTP2. The protocol format here is in text format, and here it is binary format after the compression. Multiplexing, it's one request at a time per connection, but here many streams can be open over the same connection. Head of the line blocking is present at both HTTP and TCP level, but here the head of line blocking is present at the TCP level, avoided by streams and frames. Header compression is not there, but here we use HPAC for header compression. Server push and prioritization is not present in HTTP1, but in HTTP 1.2 both are present, although the server push is limited use. It is not being used anymore. And prioritization, as we have already seen, is done using weights and dependencies on the streams. Yeah, this is the link to a doc that I have taken as a reference to create this video. You can go to this doc and learn in more detail about HTTP2. So I will be creating a separate video on demo on this HTTP2. Till that time, thank you so much, and please subscribe my channel.